In this screencast, we're going to build on our toolbox so far. And we're going to deal with reference frames. We're going to expand on what's been a really qualitative and simple definition of a reference frame so far, meaning that it's the point of view in which you observe motion, and then start putting some physical reality on this. And so first we have a physical definition of our reference frames, which says that a reference frame is a collection of at least three non-collinear points in which the distances between the points do not change with time. And so here are 3 points. We can call those points point O and P and Q. These points are not collinear, so meaning that they're not in a straight line. So we couldn't have O, Q, and P all in one line. And then the second part of this definition says that the distances between these 3 points, between OP, between PQ, and between OQ, don't change. And so with this physical definition of a reference frame, what we've essentially said is that reference frames are attached to things. So this is just like a rigid body. So a rigid body, all the points within a rigid body are going to be fixed to that rigid body, and they're not going to move in relation to each other. And then one more piece of information about a rigid body is that you need a minimum of 3 points to define a rigid body. So we would need 2 points to define a line, 3 points to define a plane. And so we can define all rigid bodies, or at least the orientation of all rigid bodies, by a plane. Because if we have a plane, then we can define a vector that's normal to or perpendicular to that plane, and that'll tell us the orientation of that plane or rigid body in 3 dimensions. So here's a vector n that's normal to this plane, and this vector can be defined by the cross product between 2 vectors that are defined by the position vectors. We'll say r of p with respect to O and r of q with respect to O. And the cross product of each of these would give us n is equal to r of p with respect to O cross with r of q with respect to O. So now with this physical definition, which gives us a vector that's perpendicular to a plane, it's giving us a conceptual idea of how we need to approach reference frames. However, we're not operational in this yet. We'd like to think in terms of 3 orthogonal directions. So let's define those 3 orthogonal directions. Let's use O as our origin and define the first direction along OQ. We'll define the second direction in our reference frame perpendicular to the plane along N. And then we'll define a third direction that's perpendicular to both of those vectors. And so now we have 3 orthogonal directions, and we have our directions that are going to define a 3-dimensional Euclidean space. So now let's name the reference frame. Let's call it reference frame I. This will indicate our inertial reference frame, and we write that as I is equal to, and this will be O, where O is the origin of this reference frame. And then we're going to define 3 basis vectors. We're going to call them E sub 1, E sub 2, and E sub 3. Now recall that when we put a hat on top of a vector, that this is indicating that it's a unit vector. So we need to come up with 3 unit vectors, E1, E2, and E3, that are defining this reference frame. And so let's call this direction from O to Q the one direction. And so our basis vector, we'll draw it along the direction that we've defined here. That's E sub 1. And this basis vector, E sub 1, is going to be equal to the position vector, RQ with respect to O, divided by the magnitude of the position vector, RQ with respect to O. And so this is our definition of a unit vector. We now have a unit vector pointed along this line, O to Q. And now for our second vector, E sub 2, we'll define that along the direction N. So here's E sub 2. And so if it's along the direction N, to make this a unit vector, E sub 2 is going to be the vector N divided by the magnitude of the vector N. And we know that N is equal to the cross product of RP with respect to O cross with RQ with respect to O. So this ends up being RP with respect to O cross with RQ with respect to O, divided by the magnitude of that same cross product. And now we have one more vector to define that's orthogonal to E1 and E2, and that's E3. And what's nice about this is because now that we already have E sub 1 or E sub 1 and E sub 2 already defined, E sub 3 is equal to the cross product between E sub 1 and E sub 2. So now what we've done is we've taken this physical definition saying that our reference frame is a collection of at least 3 non-collinear points in which the distances between the points don't change with time, and we've turned this into 3 vectors, E sub 1, E sub 2, and E sub 3, and we've defined a point that's the origin of the reference frame, and that's given us our operational definition. And our operational definition is just saying that a reference frame is defined by 3 orthogonal unit vectors and a point, or the origin, which is fixed in the reference frame. And so now in all of our problems, we're going to define an origin of the reference frame, and we're going to define 3 orthogonal unit vectors which allow us to then work these dynamics problems.